Hello friends, I welcome you all to the next lecture of the subject Infrastructure Engineering and Construction Techniques. So from some lectures we had started with unit number 2, that is railways. Under that we had gone through the various types of rail joints along with the types of gradients which are provided on railway track or permanent way. So in this lecture we are going to discuss the various terms that are used in design of a permanent way. So these definitions are super elevation, equilibrium cant, equilibrium speed, cant deficiency, cant excess, step speed on curves, and concept of a negative cant. So we will discuss these definitions one by one, starting with super elevation. So this super elevation is also known as cant, and it is the difference in height between the outer and inner rail on a curve, and it is generally provided by gradually lifting the outer rail above the level of the inner rail. So here figure 1 shows super elevation between inner rail and outer rail. So here you can see this is a inner rail and this is a outer rail. So here you can see the difference in level between these two rails is as shown in photo or a figure. Here you can see this difference is near about 5 inches. So it is provided by gradually lifting the outer rail above the level of a inner rail. So this is outer rail which is lifted over the above the level of a inner rail. Here you can see these are the curves with super elevation. Figure number 2 shows the curves with super elevation. So the main functions of this super elevation or cant is to ensure a better distribution of load on both rails. So for a better distribution or even distribution of a load, it is necessary to provide a super elevation on curves. It also reduces the wear and tear of the rails and rolling stock. It also neutralizes the effect of a lateral force which are acting on a rail section, and it provides a comfort to the passengers. If we see the next point, it shows the relationship between super elevation E with gauge G, speed V, and radius of curvature R. So before obtaining the equation of super elevation, the notations used are: capital W is weight of moving vehicle in kg, small v denotes speed of vehicle in meter per second, capital V denotes speed of vehicle in kilometer per hour, capital R indicates radius of curve in meters, whereas capital G indicates gauge of track in meters. Small g indicates acceleration due to gravity in meter per second square, and alpha is the angle of intersection. And S, capital S is the length of inclined surface in meters. So the super elevation E can be obtained by using the formula GV square upon GR, and this value of E is in meters where small v is in meter per second. So if we have to convert this v in kilometer per hour, so if we will get a equation as super elevation E is equal to G into 0.278 square divided by 9.81 R. So if we simplify this equation, we will get the value of the super elevation as E is equal to GV square upon 127 R, where the V, that is capital V, is in meter, and this equation is known as equation number 1. So equilibrium cant is nothing but the super elevation or cant which is obtained from equation 1 is known as a equilibrium cant, and when the lateral forces and wheel loads are almost equal, the cant is said to be in equilibrium. Therefore this equilibrium cant is provided on the basis of an average speed of trains. So this equilibrium speed is nothing but, on some railways the super elevation is provided for maximum speeds if most of the trains are using the existing track are fast trains. So for fast trains the super elevation is provided for maximum speed. However, the majority of Indian Railway provide super elevation for equilibrium speed or average speed under average conditions on level track as follows. So we will just discuss the various types of speed that are used, where the first case is where the maximum sanction speed of the section on BG and MG is over 50 km per hour, that is Vmax is greater than 50 km per hour. So in that case, the average speed can be obtained by using the formula average speed is equal to 3 by 4 into V max, or shape speed on curves given by the formula. So from these two, we have to get the average speed from equation 1 or 2, whichever is less. The second case is where the maximum sanctioned speed of the section on BG and MG is over 50 km per hour or less, that is Vmax is less than or equal to 50 km per hour. So in that case, the average speed can be obtained by using the formula average speed is equal to Vmax, or shape speed on curves given by the formula. So from equation 1 or 2, whichever is less will give you the average speed. The third case is on some railways, weighted average is calculated for finding out the equilibrium speed of the trains. So this equilibrium speed can be obtained by using the formula N1V1 plus N2V2 plus N3V3 divided by summation of N1 plus N2 plus N3. So this can be simplified as summation of small n into capital V divided by n. So the notations used are N1, N2 and N3 denotes the number of trains running on track at speed of V1, V2, V3 respectively, whereas capital N represents the total number of trains on the track. Next is limits of superelevation and cant deficiency. Normally, the maximum value of the superelevation according to the Indian Railway Board is around 1/10 to 1/12 of the gauge. Therefore, the values of maximum superelevation prescribed on Indian Railways are as follows. So, maximum superelevation for BG is equal to 1/10 of 1.65 meter. So, it comes out equal to 16.5 centimeter. For BG, it is 1/10 of 1 meter. Therefore, it comes out equal to 10 centimeter. And for NG, that is for narrow gauge, it is 1/10 of 0.76 meters, that is 7.6 centimeter. So these are the limits of superelevation and cant deficiency. Next is the maximum permissible speed. So this is the highest speed permitted to a train on a curve, taking into account or taking into consideration the radius of curve, actual cant deficiency, cant excess and the length of the transition. So these are the various factors which affects the maximum permissible speed of the train on a curve. On the curves where the maximum permissible speed is less than the maximum sectional speed of the section of the line, permanent speed restriction becomes necessary. Therefore, cant deficiency occurs when a train travels around a curve at a speed higher than the equilibrium speed. Whenever the speed of the train is higher than the equilibrium speed, then it is called as a cant deficiency. So this cant deficiency is nothing but the difference between the theoretical cant required for such high speeds and the actual cant provided. So here table shows a allowable cant deficiency in which you can see the column 1 indicates a gauge and second column indicates the type of railway lines and third column indicates the normal cant deficiency provided in mm. So here for BG, that is for a railway line A and B, a cant of 75 mm is required, whereas for C, D and E type of railway lines a normal cant of 75 mm is required. And for MG and NG, the values of normal cant is 50 and 40 mm respectively. The next term is the cant excess. Cant excess occurs when a train travels around a curve at a speed lower than the equilibrium speed. So when the train travels at a speed lower than the equilibrium speed, then it is called as a cant excess. Therefore, cant excess is the difference between the actual cant provided and the theoretical cant required for such a low speed. Therefore, the limiting values of cant excess have also been prescribed, and cant excess should not be more than 75 mm on broad gauge and 65 mm on meter gauge for all types of rolling stock. The next point is the safe speed on curves. So, for all practical purposes, safe speed means a speed which protects a carriage from the danger of overturning and derailment and provides a certain margin of safety. So, the various factors which affect the safe speed on curves are as follow. The first is the gauge of the track, the second is the radius of the curve, and third is the amount of super elevation. Earlier, the safe speed on curves were calculated empirically by applying the Martin's formula. So now we will see the Martin's formula for BG and MG. The safe speed V in kilometer per hour is given by Vmax is equal to 4.35 under root R minus 67, and it is subjected to a maximum speed of 50 km per hour. So for a speed of 50 km per hour, we can get the value of Vmax by using this formula. So this is a safe speed on curves. The next important point is the concept of negative cant, which is also known as negative super elevation. So here you can see a figure shows there are two tracks intersecting each other at point P. This is a branch line and this is a main line. So when the main line lies on a curve and has a turnout of contrary flexure which is leading to a branch line, the super elevation necessary for the average speed of trains running over the main line curve cannot be provided. In figure 1, AB, here you can see AB is the outer rail of the main line curve which must be higher than CD for the branch line. However, CF should be higher than AE, or point C should be higher than point A. These two contradictory conditions cannot be met within one layout. So, instead of outer rail CF on branch line being higher, it is kept at lower level than rail AE. In such cases, the branch line curve has a negative super elevation and therefore speeds on both tracks must be restricted, particularly on the branch line, and this is called as a concept of a negative cant or negative super elevation. So with this we will stop here and will continue in the next lecture. Thank you.